Welcome back, everybody, for another deep dive. This time, we're taking a look at a pretty interesting new approach to multi-agent pathfinding.
Yeah.
It's called Shared Recurrent Memory Transformer, or
SRMT.
SRMT. That's right. Now,
It's a mouthful.
it is a mouthful,
Sure.
but luckily, we have our expert here to help us break it all down.
Absolutely.
So, you shared this research paper with us titled SRMT, Shared Memory for Multi-Agent Lifelong Pathfinding.
That's right.
Now, this looks really interesting. Just imagine a world full of self-driving cars, delivery robots, you name it,
Yeah.
all trying to navigate these complex environments without running into each other.
Right.
That's basically the whole challenge of APF in a nutshell, right?
Absolutely. It's a problem that's been, kind of a thorn in the side of researchers for a long time. The traditional approaches to multi-agent pathfinding, they often run into this thing that we call state-space explosion.
Oh, okay.
Basically, as you add more agents and the environment gets more complex, the number of possible paths just explodes. And it becomes really, really computationally difficult to actually figure out the best solution.
So it's kind of like if you're trying to solve one of those giant Sudoku puzzles where every empty square has like 1,000 possibilities.
Exactly. It just blows up in your face.
Yeah.
And that's where this whole idea of shared memory comes in.
Okay.
Like, what if the agents could actually learn from each other's experiences,
Yeah.
and avoid making the same mistakes over and over again?
Right. And that's exactly where SRMT comes into play, right?
Okay.
But before we dive into all the nitty-gritty details, I'm kind of curious. How did the researchers actually even start testing this idea out? Like, where did they begin?
Well, they started it with this really simplified scenario. It's called the bottleneck problem.
Bottleneck problem.
Yeah.
Okay.
So picture this. You have two rooms connected by a narrow corridor,
All right.
and you've got two agents, each starting in one of the rooms, and they need to switch places. They both need to get to the opposite room.
Sounds simple enough. I'm guessing that corridor is where things get a little bit tricky, though, right?
That's exactly right. It creates this classic bottleneck situation where the agents really have to coordinate their movements very carefully so they don't end up getting stuck. And to make things even more challenging, they actually gave the agents in this scenario limited vision.
Limited vision.
Meaning they could only see a small area around themselves.
Oh, okay. So they can't see the whole picture.
Exactly.
So you got limited vision, you've got this narrow passageway, and you need to coordinate with another agent. I'm starting to see why this is such a good test for SRMT.
Precisely. And to really kind of push the limits of this shared memory approach, they tested SRMT using 3 different reward systems.
Reward systems.
Yeah, think of it like different ways to give the agents feedback as they're learning.
Oh, okay. So walk me through these reward systems. Like, how do they actually work?
Okay, so the first one is called directional.
Directional?
And it's pretty straightforward.
Okay.
The agents basically get rewarded for moving towards their goal.
Okay, that makes sense.
Yeah.
You want to encourage them to head in the right direction.
Exactly.
Okay, what about the second one?
The second one is called moving negative.
Moving negative, okay.
And this one actually penalizes unnecessary movement.
Oh, okay.
So it encourages the agents to find like the most efficient path and avoid just wandering around aimlessly.
Gotcha. So it's like saying, hey, don't waste time and energy taking the scenic route.
Exactly. Get to the point.
I like it. All right, so what's the third reward system?
All right, so the third one's called sparse.
Sparse.
And this is where things get really interesting.
Okay.
In this system, the agents only receive a reward when they actually reach their goal. There's absolutely no feedback along the way.
Whoa. That's tough. So it's like they're navigating a maze in complete darkness.
Yeah.
And they only know they've succeeded when they finally reach the exit.
Exactly. And this is really where the power of that shared memory idea shines through.
Because even without that constant feedback, the agents can still learn from each other's experiences and slowly start to figure out the best way to go.
So it's like they're building this collective map of the environment in their shared memory, even though they can't see the whole picture individually, right?
It's a great way to put it.
So did SRMT actually manage to succeed in this sparse reward scenario?
It did. And this was actually one of the most exciting findings of the research.
Okay.
SRMT consistently did better than all the other methods that they tested against, especially in that sparse reward scenario.
Wow.
So even with that limited vision and the very minimal feedback, the agents with the shared memory were actually able to navigate that bottleneck pretty effectively.
That's really impressive. But let's dig into those results a little bit deeper.
Okay.
What exactly do we mean by outperformed? Like, did they measure how long it took the agents to reach their goals?
Yeah, they did. And what they found was that SRMT didn't just help the agents find a way, it helped them find close to the best possible paths.
Oh, wow. So they weren't just getting there, they were getting there efficiently.
So it's not just about solving the problem, it's about solving it in the smartest way possible, right?
Exactly. And what's even more impressive is how adaptable they found SRMT to be.
Really?
Yeah, they even tested it by making that corridor way longer.
Oh, wow.
To make the bottleneck even harder to navigate.
Okay, so how much longer are we talking here?
Oh, they gradually increased it in their simulations, Started from a reasonable size, went all the way up to a whopping 1,000 cells long.
1,000 cells. That's a serious bottleneck.
Imagine like this tiny corridor stretching out forever.
Yeah, that sounds pretty daunting.
And remember, this is all still with that sparse reward system, right?
Yeah.
So they're doing this with very little feedback.
So even when the problem got way more complex, SRMT was still able to adapt and find efficient solutions.
That's right.
That's amazing.
Mm-hmm.
Okay, so far we've mostly talked about SRMT going up against this sparse reward system.
Right.
What about those other two, directional and moving negative? Yeah. Did it perform well in those scenarios too?
It did, yeah. And that's actually another big strength of SRMT. It wasn't just a one-trick pony.
Okay.
It consistently did better than a lot of the, state-of-the-art multi-agent pathfinding methods out there across all three reward systems.
Yeah.
So it's really showing its versatility and robustness.
So it's not just about the specific reward system, it's about the fundamental advantage of shared memory when you're dealing with these kinds of problems.
Exactly.
Fascinating. Now, you mentioned they compared SRMT to other methods.
Mm-hmm.
What were some of those and how do they stack up?
Well, they tested it against some, pretty well-established multi-agent pathfinding algorithms, things like MBA, QPLEX, and other memory-based architectures as well. Mm-hmm. Some of these have been, like the gold standard in the field for a while now.
Right.
But SRMT was consistently showing, better performance, especially as the problem got more and more complex.
It really sounds like this shared memory approach is giving SRMT a serious edge.
It seems like it, yeah.
Can you give us an idea of how much better SRMT was compared to these other methods? Are we talking small improvements or like big leaps forward?
Oh, in some cases, the improvements were actually pretty dramatic.
Wow.
For example, in that sparse reward scenario with the super long corridor, SRMT was getting success rates close to 100%.
Okay.
While some of the other methods were struggling to even find a solution, 50% of the time.
Wow, that's a huge difference.
Yeah.
It's clear that SRMT is doing something really special here.
Yeah.
Did the researchers do any kind of deeper analysis to try to understand why SRMT was so successful?
They did. And this is where things get even more interesting, I think.
Okay.
They actually analyzed what the agents were learning, like their memory representations.
Right.
And they found something really remarkable.
What's that?
The distances between those memory representations were actually related to the physical distance between the agents in that bottleneck scenario.
So let me make sure I'm understanding this correctly. You're saying that the agents' memories were basically mirroring their physical positions in the environment.
You got it. It's almost as if they were building this kind of like mental map of the bottleneck in their shared memory, even though they couldn't actually see the whole thing at once.
Right.
And that shared map then let them coordinate their movements way better than if they were just relying on their own limited vision.
That's incredible. So it's not just that they're sharing information, but they're sharing it in a way that's spatially meaningful and directly relevant to the problem they're trying to solve.
Exactly.
So this spatial awareness, powered by the shared memory, seems to be a really key part of SRMT's success.
I think that's a great insight.
Okay, so we've seen how SRMT just aced this bottleneck problem.
Yeah.
But I have a feeling the researchers didn't stop there, right?
Oh, of course not.
They probably wanted to test this shared memory approach in some even more challenging scenarios. What did they do next?
You're absolutely right. That bottleneck problem, it was really just the beginning.
Okay.
They wanted to see how SRMT would perform in situations that were a lot more like, the messy, dynamic real world.
Right.
So they took things a step further and introduced this concept of lifelong multi-agent pathfinding, or LMAPF.
LMAPF.
Yeah.
All right, that sounds really intriguing, but also a little intimidating.
A mouthful for sure.
Before we dive into that, I think we need a quick refresher on what lifelong learning actually means in the context of AI.
Yeah, good point.
Can you break that down for us?
Sure. So in traditional AI, we usually train these agents on one specific task. And once they've kind of mastered that, they're basically stuck.
Got it.
But with lifelong learning, the idea is we want agents that can continuously adapt.
Yeah.
And learn new things without forgetting what they've already learned.
Okay, so it's like the difference between cramming for a single exam
Right.
and being a lifelong learner who's always trying to pick up new knowledge and skills.
That's a perfect analogy.
And in the context of multi-agent pathfinding,
Right.
this means that instead of having one fixed goal,
Right.
the agents are constantly getting new goals thrown at them, just like in real life, where things are always changing. Right?
Yeah.
Okay, so that's LMAPF, constantly adapting to new goals and new challenges. I'm definitely starting to see how this takes the complexity up a notch.
Yeah.
So what kind of environments did they actually use to test SRMT in these LMAPF scenarios?
They used a bunch of different environments to really put SRMT through its paces.
Okay.
They had everything from these like maze-like environments with winding paths and dead ends.
Oh, wow.
To warehouse environments with those narrow corridors and lots of congestion.
Okay.
They even threw in totally random environments just to see how well SRMT could adapt to the unexpected.
So they really wanted to make sure it could handle the unpredictable nature of the real world, huh?
Exactly.
What were they looking for in these LMAPF tests? Was it still all about finding the fastest path?
Well, path optimality was definitely still important, but in LMAPF, the main focus shifted to something called throughput.
Throughput.
Yeah, so basically, this measures how many goals the agents can successfully achieve over a certain period of time.
Gotcha. So it's not just about getting there, it's about getting there quickly.
Exactly.
And consistently amidst all the chaos and all the changing demands.
That's right.
All right, I'm on the edge of my seat. Tell me, how did SRMT perform in these LMAPF scenarios? Was it able to handle the pressure?
The results were, once again, really promising.
Okay.
SRMT showed that it was really adaptable, performing well across all the different types of environments, including those really crowded warehouse scenarios.
So even when things got super crowded and chaotic, SRMT was still able to keep up with all the demands and guide those agents to their goals efficiently.
Yeah, exactly. And there's this one finding that was particularly interesting in those really congested warehouse environments. When they combined SRMT with a specific kind of path planning algorithm, it actually performed even better.
Oh, really?
Yeah.
What kind of path planning algorithm are we talking about? And what was it about this combination that led to such a big performance boost?
Well, it's a type of algorithm that takes into account the overall flow of traffic, you know? It helps the agents anticipate potential bottlenecks before they even happen.
Oh, that's smart.
And by combining that with SRMT's shared memory, the agents were able to not only avoid those collisions, but also make smarter decisions about when to move and when to wait, you know?
Yeah.
Which really helped improve that throughput.
That's brilliant. So it's almost like the shared memory is giving the agents this kind of like collective intelligence, right? Allowing them to anticipate problems and optimize their movements as a group, not just as individuals.
That's a great way to put it. It really highlights how SRMT has the potential to go beyond just avoiding collisions, you know?
Yeah.
And actually make these multi-agent systems way more efficient in those complex, messy, real-world settings.
I'm really starting to see the power of this shared memory approach.
Yeah.
Before we move on, can you give us a quick rundown of all the different ways that they measured SRMT?
Sure.
We've talked about throughput, but I imagine they looked at other aspects of performance as well, right?
Absolutely. So in addition to throughput, they also looked at things like pathfinding. Especially in those larger, more complicated maps.
Makes sense.
Then there was congestion. This focused on how well they handled those really high-density situations, like those really crowded warehouses we were just talking about.
Right.
And then there was cooperation, which measured their ability to solve problems that required the agents to actually work together, like navigating those tight passages or coordinating their movements to avoid getting stuck.
Gotcha.
And then out of distribution.
Okay.
This tested how well they could adapt to completely new environments, which is super important for those real-world applications where, you know, things are constantly changing.
Right.
And then finally, scalability, which looked at how well SRMT performed as you increase the number of agents. Because, you know, in the real world, you're rarely dealing with just 2 or 3 agents at a time.
Right.
You're going to have many more.
So after putting SRMT through all these different tests, what was the verdict? What are its biggest strengths?
Well, across all of those metrics, SRMT consistently showed its strengths in two key areas, scalability and pathfinding.
Okay.
Even when it was dealing with a large number of agents and really complex maps, SRMT was able to keep up those high levels of performance, finding those efficient paths and successfully navigating all those different challenges they threw at it.
This is really exciting stuff. It sounds like SRMT has the potential to totally change how we think about multi-agent systems.
Yeah.
From self-driving cars and delivery robots to all sorts of other applications we haven't even thought of yet, right?
Absolutely. And what I think is particularly exciting is that this research, it's not just about making robots smarter, you know? It's about understanding this fundamental principle of intelligence itself.
Right.
It's about the power of shared knowledge and collective learning.
I love that. We tend to think of intelligence as this individual trait, but SRMT is showing us that intelligence can actually emerge from cooperation.
Right.
And sharing information, not just from individual brilliance.
Yeah.
This is really giving me a whole new perspective on what AI can achieve.
It really is a profound shift in how we think about these things, and it has implications way beyond just robotics, you know?
Right.
Makes you wonder, what if we could apply this principle of shared memory to other areas of, you know, human endeavor?
Oh, yeah.
Could it unlock whole new levels of collaboration and problem solving? Could it even help us tackle some of the world's biggest challenges?
Those are some big questions.
Yeah.
Definitely ones worth exploring in more depth. But for now, I think we've covered a lot of ground in this first part of our deep dive.
Yeah, definitely.
We've seen how SRMT tackles the complexities of multi-agent pathfinding. Its impressive performance in all those different scenarios, both simple and complex.
Yeah.
And its potential to not only make robots better at navigating the world, but also to teach us something about the very nature of intelligence itself.
It's been a fascinating journey so far.
It has. And there's still so much more to discover.
That's right. We've only just scratched the surface.
Exactly. So for all you fellow learners out there, stay tuned for the next part of our deep dive.
Looking forward to it.
Where we'll delve even deeper into the world of shared memory and explore its potential to completely revolutionize how we think about intelligence, collaboration, and the future of AI.
Awesome.
Can't wait.
Should be fun. Welcome back to our deep dive into the world of SRMT and multi-agent pathfinding.
I'm excited to keep going with this, yeah.
Yeah, you know, as we've been talking about these, you know, amazing advancements in robotics and algorithms, it's really striking to me how this research kind of points to something much bigger.
Okay.
You know, it's not just about making machines smarter. It's about understanding something really fundamental about intelligence itself.
That's a really interesting thought. What do you mean by that?
Well, we often think about intelligence as, you know, this individual thing. Like, it's the ability to learn, to solve problems, to adapt.
Right.
But what if a really crucial part of intelligence actually lies in how we connect and share information with others?
Okay.
You know, SRMT seems to be suggesting exactly that.
So you're saying that the success of SRMT, like, it points to this core principle of intelligence.
Yeah.
That even without, like, complex communication, the simple act of sharing a pool of knowledge can drastically improve coordination and problem solving.
Exactly. I mean, look at the results.
Yeah.
These agents, they have limited vision, right? But they're able to achieve these like remarkable feats of coordination simply by tapping into this shared memory.
Right.
It's not about individual brilliance. It's about the collective intelligence that emerges from that shared experience.
It's kind of like that saying, 2 heads are better than 1. But in this case, it's more like a network of connected minds is better than a bunch of isolated ones.
Precisely. And you know, this realization, it has implications that go way beyond just robots and algorithms.
Okay.
Think about it. What if we could apply this idea of shared memory to human teams, to organizations?
No, that's a really interesting thought. Imagine a world where, like, teams working on these complex projects had access to a shared memory system. They could instantly tap into each other's knowledge, insights, experiences.
Right.
No more digging through endless emails, no more struggling to communicate these complex ideas.
Exactly. The gains in efficiency would be incredible.
Yeah.
But it goes even beyond efficiency. Imagine the boost to creativity, innovation, when all these different perspectives are just readily available.
Yeah, and it's not just limited to, like, work teams either, right?
No, not at all.
You can think about research collaborations, community projects, even global efforts to tackle things like climate change. A shared memory system could totally change how we approach these really complex issues.
Imagine scientists all over the world working on a cure for a disease, instantly able to share their data, their findings, their setbacks.
Yeah.
Or think about communities pooling their knowledge and resources to solve local problems,
Right.
drawing on this collective memory of what worked, what didn't work.
It's kind of mind-blowing to think about all the possibilities.
Yeah.
We're talking about like a whole new level of collaboration and knowledge sharing here.
It really is exciting, isn't it? And the potential applications are pretty much limitless.
Yeah.
It makes you wonder, could there even be like a biological basis for this?
Okay.
You know, could there be some kind of shared memory mechanism happening in our own brains and how different parts of our brain communicate and coordinate?
Yeah. Now you're really taking us deep here. We're talking about potentially unlocking secrets of both artificial and natural intelligence.
That's what's so cool about this kind of groundbreaking research.
Yep.
It doesn't just lead to practical applications. It also makes us ask these really fundamental questions about like who we are and how we think.
It's making me reconsider all the untapped potential for collaboration.
Yeah.
And collective intelligence.
Yeah.
In like so many areas of our lives. And it all stems from this simple but powerful idea. Shared knowledge can really amplify our individual abilities and lead to some pretty extraordinary outcomes.
It's really inspiring to see how research like this is pushing the boundaries of what we thought was possible.
Absolutely.
But before we get too carried away with the possibilities, it's important to remember that this research is still early days, right?
Right.
There are definitely some limitations we need to keep in mind.
For sure.
As we're exploring the potential of SRMT.
Yeah.
What are some things we should be thinking about?
Yeah, it's definitely crucial to keep a balanced perspective here. One thing to remember is that this research, while super promising, it's still based on like simplified models of the real world.
Yeah. Like, for instance, the agents in these simulations, they have perfect localization.
So they always know exactly where they are.
Exactly. And they execute their actions perfectly without any errors, without any delays. And the environments they're in, they're static.
Nothing changes unexpectedly.
Exactly. It's a very controlled setting.
Okay.
You know, designed to really isolate and test those core concepts.
So it's important to remember that the real world, it's a lot messier.
Oh, absolutely.
And a lot more unpredictable.
Yeah.
Things rarely go exactly according to plan out there.
Right. So before we start, you know, imagining sleets of robots with shared memories running around, we really need to see how SRMT performs in more realistic and dynamic environments.
Like, for example, self-driving cars.
Exactly.
They have to navigate traffic.
Yeah.
That's always changing. Unpredictable pedestrian behavior.
Totally.
All sorts of unexpected things happening all the time.
Yeah, it's a whole different ball game from those nice, tidy, simulated environments.
Definitely. And this is where the next stage of research gets really exciting. Bridging that gap between these simplified models and the complexities of the real world.
Right.
That's going to require some really innovative solutions.
Absolutely.
And a much deeper understanding of how shared memory can work when things are uncertain.
I can't wait to see what they come up with next.
Me too.
Whoa.
But even with those limitations, the potential of SRMT is still super exciting.
Oh, without a doubt.
It shows us how much we still have to learn about intelligence, both artificial and natural.
It's a good reminder that we're constantly pushing those boundaries of what's possible.
Yeah.
And sometimes the most groundbreaking discoveries, they come from the most unexpected places.
I completely agree. Now, are you ready for one final thought-provoking twist before we wrap up this part of the deep dive? Bring it on. My learner brain is definitely craving more. Okay, hit me with that thought-provoking twist.
Okay, well, remember how we were talking about how the research paper doesn't actually say that SRMT guarantees those agents will always reach their destinations?
Yeah, you mentioned it's not foolproof, especially when we start thinking about all those messy real-world scenarios.
Exactly. And this brings up a really important point that I think often gets overlooked when we talk about AI and algorithms.
Okay.
It's the difference between, like, theoretical guarantees and practical effectiveness.
Okay, I'm curious. Break that down for me. What's the difference?
All right, so think about it this way. Imagine you've got this recipe for baking a cake.
Okay.
A theoretical guarantee would be like saying, if you follow these steps exactly, you are guaranteed to get a perfect cake every single time.
That's a pretty bold statement.
Right.
Even with the best recipe, things can still go wrong in the kitchen.
Exactly. In reality, there are so many things that can influence how that cake turns out. Oven temperature, the quality of your ingredients, even like the humidity in the air.
Yeah.
It can all make a difference.
So even if you have the perfect recipe, There's no absolute guarantee you're going to get that perfect cake every time.
Right. You're relying on the process and your own skills as a baker to get that good outcome.
Right.
And it's the same with these algorithms like SRMT. In theory, it might not be able to mathematically prove that the agents will always reach their goals, especially in those complex real-world situations where, anything can happen.
Yeah.
But that doesn't mean it's not incredibly effective in practice.
So it's kind of like saying SRMT is a really, really skilled baker. You might not be able to promise a perfect cake every single time.
Yeah.
But it consistently delivers some pretty impressive results.
Exactly. And, the research really clearly shows that even without those absolute guarantees, SRMT consistently does better than other methods and gets these really remarkable results in a wide range of challenging environments.
Okay, it sounds like it's all about finding that sweet spot.
Yeah.
That balance between theoretical rigor and practical application.
Absolutely. And that's something I think is really key for anyone who's interested in AI and how it's going to impact the world.
Right.
We need to be realistic about what these algorithms can and can't do, but we also shouldn't underestimate their ability to solve really complex problems and make a real difference.
That reminds me of that famous quote.
What's that?
All models are wrong, but some are useful.
Yeah, that's a good one.
We can't expect to have perfect models.
Right.
But we can aim to create models that are useful, that help us understand the world and solve real problems.
Exactly. And SRMT is proving to be one of those really useful models.
Yeah.
Pushing those boundaries of what we thought was possible in multi-agent pathfinding, opening up all these new possibilities for the future of AI.
We've covered so much in this deep dive. We've explored the science behind SRMT, the potential applications, even some of the philosophical stuff.
Yeah.
About how we think about intelligence.
Yeah, it's been a good one.
As we wrap things up, what's the one thing you hope our listener takes away from today's conversation?
That's a good question. I think the biggest takeaway is that we're at this really exciting point in the development of AI. SRMT is such a great example of how we're moving beyond that idea of individual intelligence and starting to explore this whole new world of collective intelligence.
It's a really powerful shift in perspective.
It is.
Makes you wonder, what if we could apply this whole idea of shared memory to our own human interactions, right?
Yeah.
Could we tap into that collective intelligence to solve some of the biggest problems facing the world today?
That is a fantastic question to think about. Imagine if we could all seamlessly access this collective pool of knowledge and experience.
Yeah.
Where collaboration and cooperation, they become the norm instead of the exception.
That's a pretty amazing thought. A world where we're all connected, working together to create a better future. It definitely gives us a lot to think about.
It does. And while there's still so much work to be done, research like this makes me feel really optimistic that we're on the right track.
Well said. I think it's time to wrap up this incredible deep dive into the world of shared memory and multi-agent pathfinding.
Yeah, it's been fun.
But before we go, I have one last question for you and for our listeners out there.
Okay.
If you could create a shared memory system for all of humanity, what kind of knowledge or experiences would you include? What would you want future generations to have access to?
That is a wonderful question to leave everyone with.
It is, isn't it?
Really makes you think about the legacy we want to leave behind, the knowledge and values we want to pass on to future generations. It reminds us that the future of intelligence, whether it's artificial or human, it all comes down to our ability to learn from each other, share, and grow together.
Beautifully said. And on that note, we'll leave you to ponder those possibilities.
Yeah.
Until next time, keep those learner brains buzzing.